the last talk in this session will be by Dr. Abdulov, Bottomonia production polarization in the NRQCD with kT-factorization.
Yes. Oh, can you hear me?
We can see your slides. We can hear you.
Okay. Good evening, everyone. My name is Abdulov Nizami, and today I'll talk about our work with Artem Lipatov about Bottomonia production and polarization in NRQCD with kT-factorization. Some of the results you can find in these papers. So in the last decades, the JPC and epsilon NS production have been actively studied after the discovery of strong discrepancy between theoretical prediction within the framework of Kohler singlet model and the experimental data obtained at Tevatron. There are two approaches to describe the formation of the heavy quarkonia: the Kohler singlet and the Kohler octet models based on non-relativistic quantum chromodynamics. The Kohler singlet model in leading order fails to describe the experimental data at Tevatron and and LHC. And somewhat better description is achieved when including NLO and next to next leading order corrections. So non-relativistic QCD is an effective field theory which is used to describe the production of heavy quarkonia based on the expansion in the relative velocity of the quarks in the, within the quarkonium and alpha s. Here, 2s plus 1 Lj is the intermediate Fock state with spin s, or orbital angular momentum L, and total angular momentum J, and Kohler representation A. From a long-distance non-perturbative matrix elements, or NMEs. For Kohler singlet, contribution A is equals 1, and Kohler singlet states are related to the physical ones. And for the Kohler octet states, A equals to 8, and there are a few mechanisms that can transit the Kohler octet into the physical states. So I'll tell you about that later. In the NLO NRQCD, a good description of the data on PT is achieved by fitting the NME values, which play the role of three parameters and determine the probability of quarkonium production. But the values of these NMEs obtained from different sets are very different from each other. However, until now, the simultaneous description of the PT spectrum and polarization has not been achieved. The theoretical prediction shows that the octet contribution with the transverse polarization dominates in the production of S-wave quarkonia at large PT. But this contradicts the experimental data from CDF, CMS, and LHCb collaborations. And also, the results of NME calculations obtained in non-relativistic QCD for JPC contradicts the experimental data for ETC. One of the solutions to this problem was proposed in the framework of the polarization model, which was proposed by Sergei Baranov and based on classical multipole expansion. And in this approach, it was possible to solve the problem about simultaneous description of PT spectrum polarization for the entire Germanium family. So the main goal of our research is to do the same for Bottomonia family, to study the process of S and P wave Bottomonia for epsilon NS and KBJ and P production and the polarization at high energies within the framework of the depolarization model. When considering the epsilon 3s production, the contribution from the decay of KB3P was taken into account for epsilon 2s from KB3P, 2P, and epsilon 3s, and for epsilon 1s from KB3P, 2P, 1P, epsilon 3s, 2s, and cascade decays. So to describe the perturbative production of P and TP pair, the kT-factorization approach is used with both Kohler singlet and Kohler octet contributions. And NMEs was determined using experimental data from CMS, ATLAS, LHCb at 7, 8, and 13 TV in different kinematic regions. So in the kT-factorization approach, in leading order includes high-order corrections, high-order QCD corrections in the form of TMD parton distribution function, which means transverse momentum dependent. It means that our parton distribution function not only dependent on the fraction of parton, of the momentum fraction of a parton and scale, but also on the parton's transverse momentum. These functions are computed as a solution to BFK and CFM equation, and the CFM equation also takes into account the terms proportion logarithm 1x and 1 minus x. For large x, the CFM equation is equivalent to dGlub ones. So here we apply several team gluon distribution A0, J set 1, J set 2, PB set 2, and MD. The last one was obtained by our team, and you can read about it in this paper. So in our calculations, we consider the subprocesses of fusion of two off-shell gluons into a singlet, 3s1 singlet state, into octet, color octet state 1 as 0, 3s1 and 3pj, and 3pj singlet and 3s1 octet for kb processes. And also we use corresponding projectors for S1S0, 3s1, and 3pj. The probability of quark-onion production of two quarks depends on the bound state wave function psi, where q is related to the moment of quarks and quark-onion. Then we integrate the production of the amplitude A expanded into series of Q0 and the production of the amplitude and psi. And so A is no longer dependent on Q. Then we get these two relations for S wave state and P wave state, where R is a radial wave function. And last, we need to find the values of NMEs. NME values, they are related to the wave function as this, again, for S wave and the P wave states. For color singlets, for epsilon ns and kb, NME values are well known. They can be obtained from the width of decay of quark-anion into lepton pair or from the potential models. For color octet, the corresponding NMEs are derived from experimental data. And also, I'll tell you about it later, we also try to obtain from experimental data the color singlet NMEs for kb1p. And also for p-wave states, we use this relation, so we only need to find NME values for 3p0 octet. So in this works, again, it was proposed, a new mechanism was proposed of the transition from octet quark pair to the singlet state, and which leads to the polarization of quark-onion. This mechanism was used to solve the problem of simultaneous description of both spectrum in terms of PT and polarization for the entire Germanium family. The main idea of this mechanism is that after the production of the octet states, a soft gluon with small energy about lambda QCD is emitted. This step is described by the multipole expansion dominated by electric dipole transition. In case of 3pj octet, we need one transition, and in case of 3s1, we need two transitions, first one to 3pj and then to the physical state. Summation over the polarization of incoming gluons is performed according to the kT-factorization approach, according to the rules of kT-factorization approach. For quark-onion, we use this expression. It's equivalent to standard one, but it's better for the fitting polarization parameters. For cross-section, we use for singlet cross-section for color singlet looks like this. For octets look like this. The main difference is that again we use TMD functions, which also they transverse momentum depend. They depend on the transverse moment of two, in our case, of two incoming gluons. So before the fitting values of NMEs, we find out that the shape of cross section in terms of PT is practically the same for the kb 3s1 octet and for epsilon 3s1 octet, and in all kinematic regions and at different energy. And here you can see for epsilon 3s, 2s, and 1s, with high accuracy, they still keep being constant. So we can approximate this relation with high accuracy by constants. So considering the previous relations, we use expanded data to fit NMEs and this linear combination of NME octets. After finding all the NMEs and the value of this linear combination, we use the ratio obtained by LHCb collaboration at 7 and 8 TeV. A ratio of kb to 1 to epsilon. From this ratio, we find out the values NMEs for kb0 3s1 octet, and knowing this value, known R and MR, we can find the NMEs for epsilon 3s1 octet. And from here, we found out all the NMEs values for all the Bottomonia and for all the Bottomonia. But for this, we did this for epsilon 3s and 2s. For epsilon 1s, as I said, we try to also fit the color singlet for kb 3p1 and 3p2. First, again, we find out that the ratio of kb2 to kb1 singlets and epsilon 3pj octet to kb1 singlet, they also keep being can be approximated by a constant and also with high accuracy. So again, we use this knowledge to introduce another linear combination of two singlets and one epsilon octet. And again, as in the case of MR, we extract all the NMEs and two linear combinations from the distribution of PT in the terms of PT. Then again, we use LHCb data of the ratio kb1p to epsilon 1s, and find out from this ratio. We find values for 3s1, epsilon 3s1, octet kb0, and triple 0 for epsilon, triple 0 contribution for epsilon 1s production, and the linear combination of two singlets of kb1 and kb2. And then we use CMS and LHCb data at ATV for this ratio of kb2 to kb1. And then we find out the values for kb1 enemy, kb2, and therefore we find all the enemy values for all the Bottomonia family. So here's some of the results of enemy values for 3s, for 2s, and for 1s, epsilon 1s. We compare them to the values obtained from the NLO, NRQCD collinear approach obtained in this paper. First, we should notice that all the 1s0 contributions in our case is 0 for 3s, for 2s, and for 1s. And also, as I said before, the enemy values, they're different. They depend on which TMD set we use. And as you can see, they're different from each other. So now, after finding all the enemies, we compare them to the experimental data. For example, for CMS at 7 upper histograms and 13 TV. It's data from CMS collaboration. First row is epsilon 3s, second one epsilon 2s, and the last one epsilon 1s. As you can see, within the experimental and theoretical uncertainties, we have a good agreement for all the 3 epsilons in different kinematical regions. We have good agreement in the distribution of PT. Next is, again, we use enemies to find out the ratio of kb to epsilon. Here's ratio of kb1p to epsilon 1s, kb2p to epsilon 1s, and kb3p to epsilon 1s. And also kb2p to 2s, kb3p to 2s, epsilon 2s, and kb3p to epsilon 3s. As you can see, again, we have a good agreement, experimental data within the uncertainties, except the ratio of chi2p and to epsilon 1s and chi3p to epsilon 1s. We kind of overestimate a little the experimental data, but the same thing, the same results our colleague obtained in the NLO approach. They also have a little overestimation. They overestimate experimental data. So we're here not alone. But others, all other relations, they're all good, and we have good agreement with experimental data. So for the relation of kb to kb1 also, we used data from CMS and LHCb at ATV. And also, I mean, within uncertainties, we have good agreement with experimental data. So after finding the enemy values, we try to calculate the angular parameters, lambda theta, lambda phi, and lambda theta phi, and compare them to the experimental data by the CMS and CDF collaborations. We first feed the angular distribution of the final leptons. All parameters are calculated in the 3 frames, in the frames of Collins-Soper, helicity, and the perpendicular helicity frames. And additionally, we calculated the frame-independent parameter lambda tilde. So here are some examples of our calculations for polarization parameters in the Collins-Soper system at 70 TV using the CMS data, CMS collaboration data. First row is epsilon 3s, 2s, and 1s, and from left to right, it's lambda theta, lambda phi, lambda theta phi, and lambda tilde. And as you can see, in different for different epsilons in different kinematical regions, we have either weak polarization or zero polarization. Without any restriction, we didn't put any restriction for our calculation except experimental ones. So, and for all, and not only for Collins-Soper, also for helicity and perpendicular helicity frames, we have good agreement with experimental data. So, as a conclusion, we have considered the epsilon NS and kb MP production at Tevatron and LHC in the framework of kT-factorization approach. Our consideration is based on the off-shell production amplitudes for hard partonic subprocesses, including both color singlet and color octet contribution, non-relativistic CQCD formalism for the formation of band states, and TMD gluon densities in the proton. Treating the non-perturbative color octet transitions in terms of multipole radiation theory and taking into account fit-down contribution from radiative KB MP decays, we extracted long distance non-perturbative non-relativistic QCD matrix elements for epsilon 1s, NS and KB MP mesons. We achieved good agreement with experimental data on the transverse momenta distribution and on relations of KB to epsilon and KB2 to KB1. And we find only weakened zero polarization in all climatic regions that agrees with the CMS and CDF measurements. So again, as we showed, that this proposed approach can be one of the solutions to solve the known problem of simultaneous distribution of PT spectra and polarization observables in the framework of quantum chromodynamics. So this, thank you for your attention. If you have any questions or remarks.
Thank you very much for a nice talk. Any questions? Okay, actually, I have one question. Talking about the ratio KB2 to KB1. So you explained that this ratio doesn't depend on transverse momentum. So my question is, what will happen with this ratio if we consider kC mesons?
It was done, I think, kC mesons was done in these papers. Here, all the Germanium family, and I think they're good. They have good also. Yes, yes.
That's nice. So this ratio would be flat also, right?
I think yes. Yeah.
Since, as far as I remember from experimental data, they tell that the ratio for Germanium method, it has peak near low PT momenta. Yeah, as far as I remember.
To be honest, I don't remember about kC. To be honest.
So actually, my question was, I'm pretty sure that for Germanium meson, for kC meson, this ratio, it had peak near small PT momenta in collinear region. So actually, my question was, what could be the difference between Germanium and Bottomonia mesons? See?
And different in what way exactly? In a ratio in KB to.
Yes, KB2 to KB1. It has a KC2 to KC1. It has a peak near PT equals to 0. So, and it is, as far as I remember, it is an experimental result. So my question was, what could be the reason for such difference between Germanium and Bottomonia mesons? So
I don't know, to be honest. I don't know. I mean, we used experimental data and we have this only this. Maybe if we have, for example, more PT range will be bigger. We'll have different distribution, and then we'll. But for now, it's kind of hard to answer, to be honest.
Okay, thank you very much.
Maybe I can answer.
Yeah.
Carlos here. I think the talk of Pietro showed the figure KC2 over KC1 and also KB2 over KB1 as a function of PT over M, and it is quite flat for both cases. Now, on the other hand, all of those ratios depend quite strongly on the assumed polarization. If you assume different JZ values from, for instance, plus or minus 1 for the KC1 and plus or minus 2 for the KC2, that will be one extreme scenario. Another one will be JZ equals 0 for both cases. You get very different shapes. All of them are measured. The measurement depends on the assumption that you take for the calculation of the detection acceptances. If you assume one polarization scenario, you measure something. If you assume another polarization scenario, you measure something else. Both cases are measurements. It's just that you need to know what is the assumption that you inject in the Monte Carlo used to calculate the acceptances. So saying this is experimental data, is not very useful because everything is experimental data. So first, all the ratios are flat. Second, but they depend on the assumed polarization. Assuming that the kc1 and the kc2 polarizations are zero is an extremely bad assumption. This has been excluded by the CMS measurement. The kc1 and kc2 polarizations are as different from each other as they can possibly be. So definitely you cannot just take the data from the experimental papers reported under the assumption that everything is unpolarized, because that assumption is the one that has been excluded by the measurements. We can discuss this further in the discussion session later on.
Okay, any other questions? Okay, then I think we're finished with this section.